Dear children, so in the previous lecture, we stopped at this definition, right? That is, let E be a finite extension of a field F, then the number of isomorphisms of E onto a subfield of F closure, leaving F fixed, is called the index E over F of E over F. Okay, so the number of isomorphisms of E onto a subset of F closure which leaves F fixed, that is denoted by E over F. Okay, right. So let's have a look at a corollary. If E is an extension field of F and K is an extension field of E, where K is a finite extension of F, then index of K over F equal to index of K over E times index of E over F. So let us just look at this uh, with the help of a diagram. So that is, from F to F dash, you have an isomorphism sigma, and E is an extension of F, and you have tau from E to a subfield of F closure or F dash closure, and K is again an extension of E from, zeta is an extension of, K is an extension of E, and you have zeta from K to K dash, or again it can be a subset of F dash closure. Okay, so we want to prove that index of K over F equal to index of K over E into index of E over F, right? So this is what we want to prove. All right. Now, what do we know? So, from one of the previous results, we know that the number of isomorphisms does not depend on E dash or F dash or tau or sigma. It depends only on F and E. That is number of extensions, not number of extensions. When you're extending from F to E, the number of isomorphisms from E to a subfield of F closure, that is number of tau, depends only on E and F. Okay, and that number is denoted by the index E over F. Okay, so for each sigma, there are how many isomorphisms from E to E dash? That number is known as E over F. Okay, so for each sigma, there are E over isomorphisms of the form tau of E, which fix F. Okay, so for each sigma, you can find index of E over F isomorphisms from E to E dash, which fix F. Okay, and for each tau, how many isomorphisms are there of the form zeta from K to subfield of F closure, which fix E? For each tau, you can find index of K over E isomorphisms, which fix E. So that is what, for each tau, there are index of K over E isomorphism tau of K, which fix E. Okay, so just go through it once more. For each sigma, you can find E over F isomorphisms which fix F, and for each tau, you can find K over E isomorphisms which fix E. Okay, so what does that mean? The number of ways of extending sigma to tau is E over F. Yeah, so there are E over F ways of extending from sigma to tau, and how many ways are there from extending from tau to zeta? There are K over E ways of extending from tau to zeta. Okay, so sigma to tau you can extend from E over F ways, and tau to zeta you can extend in K over E ways. Therefore, total number of ways of extending from F to K, that will be K over E times, this is product, times E over F. That is K over F equal to K over E times E over F. Okay. Now, this is a result that we'll be studying in the next module. That is, this is actually equal to, that is, the square bracket E over F is equal to curly bracket E over F. What is the square bracket E over F? In the previous module, we learned that this is nothing but, if you consider F as an extension field of E, then you consider F E as a vector space over F. Then the dimension of E over F, that is what you denote by this. This is also called index of E over F. Okay, but this denotes square bracket E colon F. It denotes the dimension of E over F, considering E as a vector space over F. And what does this denote? This denotes the number of isomorphisms from E to a subfield of F closure which leave F fixed. And in the next module, we'll be learning that for every finite extension E of F, these two quantities are one and the same. Okay. So we are not going into the details of this proof for now, but we can just illustrate this using an example. Okay. So consider E, which is q root 2 root 3 over q. Okay. So in the previous example, we already saw that how many isomorphisms are there of q root 2 root 3 which fix q. I think this was precisely done in an example after theorem 3.4. We saw that the number of isomorphisms of q root 2 root 3 which fix q is 4. And those isomorphisms were, what is it, identity. One was identity. Then you had another one as psi root 2 comma minus root 2. Then another one was your psi root 3 comma minus root 3, and the other one was composition. I think we took it as psi root 6 comma minus root 6, or the composition. I don't remember exactly. Anyways, so these were all those 4 isomorphisms. So we have actually seen that index of q root 2 root 3 over q is 4. Okay. And similarly, you can also say that index of q root 2 root 3 over q root 2 is 2. That is, number of isomorphisms of q root 2 root 3 fixing q root 2 is 2. Those two isomorphisms will be, one is the identity and the other is your psi root 3 minus root 3, because psi root 3 minus root 3 will always fix q root 2, isn't it? Okay, so that is another isomorphism of q root 2 root 3 which fix q root 2. So this is also 2. Similarly, we can also say that q root 2 over q also has index 2. Okay, so what did we see? We just saw that q root 2 root 3 over q, this is 4. Q root 2 root 3 over q root 2 is 2, and q root 2 over q is also 2. So you can actually see that this value is equal to product of these two values, because 4 is equal to 2 times 2. Okay, so we can say that q root 2 root 3, index of q root 2 root 3 over q equal to index of q root 2 root 3 over q root 2 times index of q root 2 over q. Okay, so this is precisely what we learned here. Index of k over f equal to index of k over e times index of e over f. Okay, now in previous module we also saw that the considering q root 2 root 3 is a vector space over q as an extension of q, we saw that degree of or dimension of q root 2 root 3 over q is 4, because I think we said that the degree of the irreducible polynomial was 4. Okay, so this is also 4. Therefore, we can conclude that from this, it's not a conclusion, we can, from this example we can verify that both indexes, that is, one as a number of isomorphisms and the other as the degree of or the dimension of the vector space, both cases the values are the same. So we have verified using one example that this index is equal to this index. Okay, so that is it about this corollary. Now we are going to the last section of this module, which is the proof of isomorphism theorem, isomorphism extension theorem. So this is going to be somewhat a big proof. So we'll continue this in the next lecture, next video.